right, so now we're getting into chapter 3. Chapter 3 is where things start getting a little bit more interesting because we are going to start to talk about spinners, right? Because spinners are very, very interesting objects. He goes over again, recaps on vectors, recaps on scalars, but spinners are going to be a big part of this book because spinners are going to be the fundamental descriptors of electrons. And mathematically, they make sense. Spinor actually kind of makes sense to a degree. But physically, it's very, very hard to picture something like a spinor in our head. So for example, we can picture vectors in our head, but we cannot, at least I can't, picture a spinor in my head. I can really only deal with them on the iPad or on a piece of paper. So let's get right into it. I'm skipping a couple of pages because I think some of the pages in the book are very easy to read. I don't think they need that much of an introduction, if you will. So I'm gonna get right into the spinor part. So we've talked about vectors, we've talked about scalars. Let's talk about spinners now. So the first distinction we want to make is the difference between Vial spinners and Dirac spinners. Right? So Vial spinners versus Dirac spinners. Right? And so the Vial spinners, they're going to look a little something like this, right? So essentially what these spinners are is that they're objects such that if you deal with them in 4 dimensions, if you transform them in 4 dimensions, they actually just transform as if they were in 2 dimensions. And so in 4 dimensions, we have space and time. We have the 3 components of space, right? And our 1 component of time, making up a total of 4 components, right? That's 4 dimensions. In 2 dimensions, spinners don't have they don't have spatial or temporal components. They have 2 components though. And these 2 components are the things that transform. So they live in 4-dimensional space, but the components are not X, Y, and Z or T or anything like that. These are different components that will transform. So there's 2 types of Vial spinners. There's a left-handed and a right-handed Vial spinner. And again, these are covered in the book. We're going to call the left-handed Vial spinner chi, and I can't remember what for the life of me what this symbol is called, but this is going to be the right-handed spinner. So this is the we'll call this the left-handed spinner, and by definition, this one's called the right-handed spinner. Right. So far, we're just looking at definitions. The Dirac spinners are going to be a combination of the left and the right-handed spinners. So we can write this as 1, 0. We can write this one as 0, 1. These are small little 2-dimensional vectors, but again, they live in 4 dimensions. They're going to be descriptors of electrons or anything that has spin, as we'll see later. Dirac spinners, we're going to give them this symbol, or the book gives them this symbol, and they are a combination of the left-handed vial spinner and the right-handed vial spinner. So this also equals 1, 0, 0, 1. Right? Because if we cut this down the middle, we see that we have chi and we have the other one here, right there. So that's what, so this is our Dirac spinner. These are our Vial spinners. So we have 2 Vial spinners and 1 Dirac spinner. These spinners, they are functions of space and time, right? Even though we've written the component, even though I said that the components were not, they're not dependent on space and time, much like a vector like this would be. Right, that's a vector. That vector, everywhere in space, there's one of these vectors, right? That's not how this goes for spinners. For spinners, we have, if we want to make them functions of space and time, we simply say that, this is how the book writes it, for a left-handed spinner. Now we're using this symbol now as sort of a canonical symbol to represent left-handed, right-handed, and Dirac spinners now. And we're going to put a subscript if we want to identify if it's a left or a right-handed spinner. But we're making them functions of space now and time. And the way we do that is we say that this is chi times x mu x mu, right? Similarly, and so to be more complete, we have x mu is a function of space, and this is chi times x mu, like this. Similarly, we can have a right-handed spinner, r, and it's a function of space and time. And you guessed it, it's just going to look like this. Right? So we could put any vector in any of for x mu, and we can get what the value of the spinner is. And think about what this does for a second. This is a way of adding more complexity to our fields, right? Because imagine you had just a vector that looked like this again, t, x, y, and z. We could put one vector at each point in space and time here, right? But if we have a spinner, imagine we had a field. Imagine this is a left-handed Vial spinner field. We have x mu, right? So x mu, this is going to be a vector, right? X, y, and z. This is going to be a vector. But then we're also going to be able to multiply this by a chi here. Remember, chi was being this thing that had 2 components to it. So we actually have, imagine this point here. Imagine this point here was 2, 1, 1, 1. Right, well, at this point then, we're going to have the value of our left chiral spinner field is going to look like this. I'll undo that really quick. It's at 2, 1, 1, 1, what does that equal? That equals 1, 0. Actually, I just realized right now my face might be going over this. This is going to equal, write this out again, at 2, 1, 1, 1, this is going to equal 1, 0 times 2 squared minus 1 squared minus 1 squared minus 1 squared times, and that's how that goes, right? So this right here, this is our x mu. We're squaring because we have the mu on the top, mu on the bottom. We've seen how this goes already in previous videos, but this is going to be 1, 0 times 4 minus 1 minus, so 4 minus 3, that's going to be 1. So at this point, at 2, 1, 1, 1, we have this. We have this spinner, right? Because that's just that times 1. Similarly, we can do the same thing for right-handed spinners, or chiral spinners, if you will. So that's how these things are functions of space and time, and like you've guessed, we can write down also our Dirac spinner as a function of space and time, and that's again going to be chi, and that's going to be x mu and x mu, right? So what do we have? What's our picture here? Our picture looks like, imagine now we have, I'm going to erase some of this. I'm going to erase the whole thing actually. Imagine, so we have, say this is our left-handed viral spinner field. Here's our right-handed Vial spinner field, and then we have our Dirac spinner field. Okay, these are different fields, right? These are physically different fields. We have different fields for left-handed and right-handed spinner fields, but they're connected to each other by the Dirac spinner field, right? And so that they have some internal connections with one another, right? So you can't just freely pick one field, or you can't just freely pick all three of them, because there is some connection between the two, and that connection lies in the Dirac spinner field. And we're going to get deeper into this later. This is just an introduction into spinners. So the way by which we convert spinners, much like we did for converting, much like we did this operation, if you recall, I'm going to go back to black. If you remember, recall the connection between these two objects is by the Minkowski metric, right? And the way we did that was like this. Here's our Minkowski metric, and it looks like that. We're summing over indices. We've gone over this before already. I'm not going to go over it again. But we use the Minkowski metric to go between upper and lower indices. For spinners, we use a different type of metric. This is sort of it's called the Levitovita metric, if you will. I'll just call it that for right now. I don't want to confuse us with tensors and all this kind of stuff. But chi A, so we have a component. This labels this labels a, this is this is a spinner, a left-handed spinner. This, we use this symbol instead of eta, and we do our conversion like this, right? So if we want to multiply the spinners together, if we want, so much like we did this, well, this is equal to the Minkowski metric, again, times, oops, my pen keeps on going to, mu nu, right? This is going to be x nu and x mu, right? So then we can multiply these together, and all we have to do next then is also apply the Minkowski metric into there. Similarly, if we want to multiply to, or we want to find the inner product between a spinner and itself, we use this guy right here, right? So if we did something like this, A, we would just have to use this symbol instead, and this is going to be AB, and these are supposed to be chi's. This is supposed to be a chi, this is supposed to be chi, and that's going to be A, and that's going to be a B. Right? I think I need to swap that around. That should be fine because, yeah. So this is the inner product between the two. We just have to multiply the Minkowski metric if we want to do that. Not the Minkowski, this other metric. And that is, so what does this look like? This symbol. It gives it in the book. This symbol looks something like this. It's an anti-diagonal matrix. Right. Whereas if we compare it again with the Minkowski metric looked something like this, right? If you remember. Fill in all of our zeros just for the sake of consistency. And this was our mu nu. This is what these guys look like, right? So this is our, this is sort of our metric, if you will, the way we convert between upper and lower indices. We do the same, that's how we do this with spinners, right? So this is a tool we use for spinners, this is a tool we use for vectors, okay? Okay, so now we want to talk about how these spinners will transform. So these spinners transform very interestingly. This is where things get a little bit weird, and I'll just cut to the chase here. So spinners, as we've all heard, if you haven't heard yet, they rotate very weirdly, right? Because the idea that if you heard already is that if you rotate a spinner once, it doesn't come back to itself. So if you rotate, in other words, if you rotate it by 2 pi, it doesn't come back to itself. You have to rotate it by 4 pi in order for it to come back to itself, right? Because here's why. So the rotation matrix that we're going to use to apply to spinners, this is what makes them unique. This is what gives them their own field, right? Is that the rotation for left chiral spinners as a function of the degree of rotation is equal to the rotation for right chiral spinners, again as a function of the degree of rotation, that's a phi, is equal to a matrix that looks like this. Cosine of 2 pi and cosine of, not 2 pi, but pi over 2, I sine pi over 2, and I sine phi over 2. That's our matrix. That's our rotation matrix. Now this, you might think this is weird. It looks like a rotation, right? It has everything. It sort of screams rotation a little bit. But we have these eyes in there. What is this? If we just take a look at this, and maybe we can leave this up as an exercise, if you will, and I've done this. Verify to yourself that this is a unitary matrix, right? Because if you remember, unitary means this is a condition for unitary. We take the transpose, or the complex conjugate of this matrix, and multiply it by itself. It should be the same thing as taking the matrix and multiplying by its complex conjugate, which should be equal to the unitary matrix. And I've done this already. I think it's a fairly easy, if you know how to take the transpose and all that, to find if you've taken linear algebra, for example, and I'm hoping you have if you're in a course on quantum field theory. But I would urge you to maybe verify this to yourself, because that's what makes these rotations special, right? Is that the rotations that spinners undergo are unitary rotations. Okay. The boosts, if we want to boost a spinner, these are not equal to each other. So the boost for a left chiral spinner is a function of something we're going to call phi. And he defines what this is in the book. I can't remember off the top of my head what it's actually called. Here, I can actually go to it. These phi's are called, I'll tell you what page it's on. These phi's are called, I'm getting close to the page here. The rapidity. So phi is the rapidity of the boost. And these matrices look like this. E to the phi over 2, e to the phi over 2, where this symbol is equal to the inverse tangent, or the arctan, of v over c. That's the velocity divided by the speed of light. And he just gives this to us. We're not going to derive this, because it's not in the book, and I'm following the books. So there are books out there that help us get to a derivation of this, but this book doesn't, and I'm going to follow the books for each video I do. And then there's a minus right here, and B, the boost for a right chiral spinner is equal to e to the minus over 2, e to the 5 over 2, 0 and 0, like that. So just by looking at these, we can say that B of AB as a left chiral spinner as a function of phi is equal to BAB of the right chiral spinners, but as a function of negative phi. Because if we put the negative in there, we just swap the two entries in the matrix and we get something that looks like this. So that's an interesting property, right? Also, as I've said, R we can just take of the rotation at 2 pi. Well, it's at 2 pi is going to be cosine of 2 pi over 2, so that's going to be pi. So all these arguments are going to be pi. I sine of pi, I sine of pi, and cosine of pi. All right, well, cosine of pi, if we remember what cosine is, we can draw it out. Right, so that's a bad drawing, but you get the point here. Cosine of pi is going to be, let me draw my draw tool out. So remember, this was 0, and this was 2 pi. So right here is pi. So cosine is going to be -1, right? So -1, -1, and then sine of pi, if we remember, looks like this. Here's our 2 pi, and here's our 0. So here's our pi. Those are going to be zeros. Look at that. We have -1, -1. So we go around once, and we don't arrive at, we go around 2 pi and we don't arrive at the original starting point, right? We don't arrive there. We have -1, -1. We don't have +1, +1. So we have to, so our argument has to be 4 pi, RAB of 4 pi of chi. Well, that's going to equal 1, 1. Because our arguments inside are going to be 2 pi. Right. So this is a very interesting thing. Again, the idea here is you have this little spinner, and you're boosting the spinner. So you're boosting the spinner, but if you boost a spinner at a rapidity, or not boosting, I'm talking about rotations. So if we rotate a spinner, it looks like we don't come to the same location, right? You could think of this as sort of dancing on a Mobius strip, if you will. Not dancing, but walking around on a Mobius strip. Mobius strip only has one side. If you go around the Mobius strip and you come back to the same point, you're not at the same point. You're actually on the opposite side of the Mobius strip. You have to go around the Mobius strip another time, if I remember this correctly. Yeah, because then you arrive on the other spot of the spot you were originally on, which was the second spot you landed on. Again, a little bit confusing, but this is these matrices that we've discovered they're transformations nevertheless, right? but they're weird transformations in that they have these weird topological properties to them, right? And this is going to become very interesting to us later on when we do a little bit more advanced stuff. Perhaps not in this book, but in other books. And the last thing we want to cover is this idea that if we take a complex conjugate of a spinner and we perform an sort of an inner product, if you will, between a right-handed and a left-handed chiral spinners, we can verify this, that this is the same thing. Here's our new chiral vector spinner, still complex conjugated, and here's our new left chiral spinner. This is equal. He actually goes through a very good place in the book where he shows this. This is just equal to the same thing as what we originally started with, right? And this derivation in the book is on page, I know it's in here somewhere, page 99. So if you have the book, you can see how this works. This all really sort of depends just on the nature of the boosting matrices. I don't want these videos to be too long. So if you have the book, you can verify this with yourself. If you want me to go through it, I am opening up my Patreon page, cleaning it up a little bit. It hasn't really been touched in a while. And we'll be able to go over this if this is something that you're interested in going through. If you don't have the book, or if you find the derivation of the book to be maybe confusing or something like that, then I'll plan on going over this. But let's look at our bird's eye view one more time of spinners, because these things are weird objects, man. These things are extremely weird. So we have, again, that we have left and right chiral spinners, and we have a Dirac spinner. We haven't talked about Dirac spinners that much, but we will a lot later on. We looked at how we can convert between spinners using these metrics. We have a Minkowski metric. If we were the analogy for the Minkowski metric is this Levitovita metric, and it looks like this. We talked about rotations and how rotations again lead to these very interesting topological properties of spinners. We talk about boosts and how the boosts are related to each other by the negative of the argument, right? So a boost for one spinner in one direction is equal to a boost for a spinner in the opposite direction, basically. And that's right here. And this all sort of comes out of the fact that these matrices look like this, right? These are exponential matrices where we have the arctan of the velocity divided by the speed of light. The last thing, very, very last thing, I just want to talk about the physical nature of this really quick. These are going to be used to describe electrons, right? Spin is going to be this property that we're going to look at a little bit more later on, where we have spin of 0. We can have a spin of 0. We can have a spin of 1/2. We can have a spin of 1. These are going to be the fundamental building blocks of nature, if you will. 0, this is going to be Higgs, right? This is going to be the Higgs particle. When the book doesn't really go over the Higgs mechanism that much. I mean, it does a little bit, but we're going to focus mostly on spin 1/2 particles. These are electrons, quarks, muons. This is the smallest possible value for angular momentum. And all of these things have mass to them. Right, so these things have mass to them. And then the spin 1 particles, these are going to be the force providers, if you will, or the interaction providers. These are going to be photons. So photons of light. You know, I have my front yard, there's light back here. And then gluons, right? Gluons. And these are going to mediate the electrodynamic interactions. So electrodynamic interactions. And these guys are going to mediate the chromodynamic interactions. Interactions. And that is going to be, that's sort of a summation on particle physics, if you will. This is, and these spin objects, these left chiral spinners, and these right chiral spinners, and these Dirac spinners, these are going to be used to mathematically represent these objects and these objects. And with that, let's continue on with chapter 3 in the next video, where we will be talking about waves. This is going to be section 3.6, and we'll also be talking about something that is sort of near and dear to my heart a little bit. I think these are very interesting: gauge fields. Gauge fields, they can be a little bit difficult to understand at first, but they're going to give us some good insight as to what curvature means. They're going to give us some good insight as to, you know, I won't spoil it. I don't want to spoil it. So again, in the next video, we're going to be talking about waves, and the video following that, we're going to talk about gauge fields. So I'll see you guys in the next one.